Welcome again to this session where we will dive into principal component analysis hands-on, where we will actually look into the code side, trying to find a bit what are the covariance metrics in the code, how we can extract eigenvalues, eigenvectors, how we can draw them with point cloud so that we have a better grasp about what we are dealing with, and also for scientific experiments if you want to show some stuff. And then down the line, we will want to export that as a feature and maybe have the point cloud with the PCA features, okay? This is an optional part. It's to give you all the necessary understanding about this very important concept, because you can use that as a feature engineering part, feature extraction part, or dimensionality reduction. Okay, so basically now we start again with a 3D point cloud, which is one entity. So if we have a point cloud with a lot of segments, in our case, it will be one segment that we will take as an entity. And from that, we will want to extract the three principal directions of its point distribution. So basically, looking at the point sample, we want to find the maximal variance direction, then the second maximal, and then the third. And all of them are orthogonal to one another. So that's very handy for the further processes. Okay, so let's get started, shall we? First big block, data preparation. So first off, we will here import the libraries. That's the first element. Then once we imported the libraries, we will load that in a point cloud variable, as always. You know there's two steps, the data preparation step. Then we move on to initial experiments. And here, the first thing that we'll want to do is to split the point cloud formed by the clustering method that we had. So for now, what we have is not a lot of files. We have one big point cloud with a label, which is the cluster label. So depending on what you want to take, DBSCAN, KNN, clustering, or HDBSCAN, it's up to you. In my case, I took the result of DBSCAN, and I want to split the initial point cloud into its individual groups for processing them independently. So that's a very common strategy where we have the data, we split, and we apply some function on it. And that's exactly what we will do after. We will apply principal component analysis, or referred as PCA, to each of these clusters. Okay, so the initial experiments are done, and then what we will want to do is to go into the data visualization side for this little bit of experiments. So first we will create a 3D plotting scene for scatter and quiver plots. So I wanted to show you that because it's very nice if you know how to handle that with Matplotlib. You don't need to go in another software to make some visualizations. Then, once that is set up, we move on to filling the plot with both vectors and point clouds, right? So that says what it says. And then, once we did all of this, we will create actually two functions. So the first one will be DrawPCA, to be able for you to draw PCA in loops, like in an easy fashion. And then the second will be a custom PCA function that will actually take points and apply PCA on it, okay? So once that is all done, we go into the data analysis part, where we will define first an iterative loop to export images of the PCA for n number of clusters, okay? And then that you will be able to have a bit of a grasp of the visualization side. And then we will define, so that is not exactly directly used in the pipeline that I show you in this course, but it's very useful if you want to do some feature extraction and use these features for further processes. So we will actually define a feature extraction loop and apply that to each cluster based on PCA. And then the last part is data export. So we will export the data with the Eigen features, okay? And all of this is detailed, of course, in the handout that you will find below. And now, if you will, we will get started coding. So again, you can put the video on the side, take your favorite IDE, take the code part that I prepared for you. So it's called underscore course, and that is the live that I will be doing. The same, it's starting for you. All right, so let's get started, shall we? So first, importing the library. Here, I want to highlight a very important library. If you didn't use it yet, it's called Panda. If you didn't, you have to install it. So either with your Anaconda or your pip install Pandas, or Conda install Pandas as well. So import NumPy, as always, Pandas, Matplotlib, and this time no Open3D. And the time is just for performances analysis. Here, the little thing that I put plt.rc params figure.dpi equal to 600. That means that whenever you will plot something, within your IDE here, you will get this 600 DPI, which is nice enough to grasp. It's actually very, very high DPI number. All right, so importing library is done. Now we will load point cloud with pandas. Okay, so the data folder on my side, as always, it's expressed relatively. It's in the results, and the dataset will be the one that I took out from DBSCAN, so ransack outliers dbscan.xyz. And to load a point cloud with Panda, it's pretty easy. So it's an ASCII file, so I will use the read CSV function. And as always, data folder plus, you have other way, you can do join and things like this. I like this style because it's pretty easy to read. I give a delimiter, which will be, in our case, that. No, I think I put that, yes, as always. And that is where it's very nice with pandas. You can load things with the names of the columns, right? So each thing, you can load it in a specific column. So in that case, it will be X, Y, Z, and label. See how I put all the names within bracket by just separating with commas, okay? And I actually do not want to have a header, so I put header equal to none in the file because it does not have a header. And the last thing that I prepared here is actually to ensure that whenever you will load, if you load this way, all the values will be interpreted on the fly, and they will not be as integer because these are not integer, so all of them will be the same. But the labels are integer, so make sure to change the type of this column by just replacing it. So I call it again dot as type integer, and this way we are good to go. So first element that I will do, of course, is to launch it to be sure that I'm in the right folder of working. It will not work, that's okay, that's what I wanted. So now I can run bits by bits. So the first part, run current cell, okay, we imported everything. Now loading, so I just do that. And we will call PCD now, which was loaded with pandas. And you see what is really nice is that you have actually the indexes on the left, the X, the Y, the Z, and the label as integer. So everything's looks very, very nice. What I could do is, for example, if I want to check the X, you just do that. I call PCD of X, and it will extract immediately the column X. So that's why it's very handy then after to play with the different elements. Okay, we are good to go on this part. Now let's move on to preparing the clusters. So here, basically what we want to do is, if you check here in the console, the label, we have a label for each of our points. So it will be very handy just to create the clusters, to group all the similar labels in a cluster, right? Because that's what it is. And to do that, we have a function called group by within pandas, which is very handy. And you can just take your panda data frame, you put group by methods just behind, and you give in bracket, that's very important. Yeah, the styling is a bit weird sometimes with pandas. You just give the name of the column you will want to use to group element. So I will just do that, and that's done. So it's very easy this way. And now if I call segments, you see that we have a generic data frame group by object, some methods to get element. So let's say I want to have an idea about what is within exactly the second or the third cluster. So I will do that segment.get_group, and I will take in bracket the number 2, and it will basically go back the panda data frame and extract exactly the indexes with all the values within it, and you can play with that how you like. And then another thing that you can do, if you just want the indexes, so this side, you can just do segment.groups, and you take in bracket the number 2, or in these things, and it will give you an index type element. And then if you want to change that, you can always change the type as well. Another thing, if I take this get group of 2, I think if I do dot index, yes, it returned exactly the same thing as above. So you have this possibility, okay? Now we prepared our cluster, we will apply to each of them a function. So as always, we test on one, and when that works, we'll do the loop afterwards. So apply some operation to each of those smaller tables with PCA. So my cluster that I will want to get, let's say that for this time, we will get exactly the segment group by, okay, and we'll take the third one just to change. And here, be mindful, we will want to select only the coordinates, right? So for this, that's to select elements within, and then we want to actually define which column we will want to have. Okay, so it's X, Y. If you do not have these two brackets, it's not brackets, it's there's a crochet. I don't have the word, sorry about that. But yeah, once you have that, the cluster will be loaded exactly from this get group, and you will have exactly what we have here, but filter only on X, Y, Z. Okay, I can show you what it means. Just copy and paste. Hop. Yeah, you see, that's exactly what we have. Now, let's compute the mean, because for the PCA, something that is important to do, especially for the processing, is to center everything, to have something normalized thereafter. So the first thing to normalize here, we'll just, of the cluster, we'll compute the mean. So for that, it's very easy with numpy, numpy.mean, and we pass the cluster that we just computed above, and we say axis 0. You know what that means. It means that we will reason at, let's say, the full line level down the line. Okay, else it will export only one number for everything, which is not the case. We want to have the mean of X, Y, and Z. Okay, so that is good. Then cluster norm, for this part, then it will be cluster minus M, so that is the cluster normalized. Okay, so we'll subtract the mean to each of the points within the cluster, and that is where NumPy is very efficient for vectorizing the operation. And now we dive into the covariance matrix. If you remember, the covariance matrix will be from where we will export the eigenvalues and eigenvector of the principal component analysis. So very easy with NumPy again, np.cov, and then cluster underscore norm. And the little trick is you have to transpose that to get the covariance matrix. Now we will export the eigenvalues and eigenvectors, and for this also very easy, we will use linear algebra, so it's shortened to linalg.eig, and here again we take the cov and we transpose it. Okay, so that's it. That's how we will get, let's say, our eigenvalue and eigenvector. I will just run that to give you an idea about what we get. It's working very nicely. And now, if I show the eigenvalue, array of 5, 55, 0.02, 0.77, and eigenvector. So it looks like it's working. So u, v, y. Okay, so there is one thing I want to highlight here. You see that the first eigenvalue is 5.5, the second is 0.02, and the third is 0.77, and some stuff behind. So one thing that is very important is to know that the, let's say, lowest eigenvalues corresponds, and the eigenvector that corresponds to that is the normal of this specific subset of points. It's a very important concept, which means that it's important to sort out the result for our operation, right? And what I like to do is to sort out things in the ascending order. So from the highest to the lowest element. So that means that the third eigenvalue is linked to the normal vector, okay? And the maximum variance will be the first eigenvalue, okay? So for that, I will show you the argsort function, which will sort elements, np.argsort. We will take the eigenvalue because this is what guide which vector is the most important or which variance is maximized. And to have that in the ascending order, we will just do that, because if I do that, let's see what we get. It returns the indexes of the sorted in a specific order. So that will be the first element, then that will be the second element, and that will be the first. And what we want is the opposite. So we want first the biggest element, and then at the end the lowest element. So sorry, it's descending order, but you know what I mean, hopefully. Sorry about the confusion. So now eigenvalue, once we have these sorted indexes, we will just pass that to make sure that the eigenvalue is sorted. So that's a little trick, but very efficient sometimes if you need to sort stuff. And here for the eigenvector, same thing, except we want to be mindful that we will take, you know, there are 3 lines, so we want to take everything in the line before sorting. So we sort on the second place here, and that's it. So now if I run this cell again, very nice. If I do eigval, we are sorted descending, and eigvec, it's following exactly the same thing, which means that this is the normal vector. Okay, and that's the first axis and that's the second axis. It's that simple. So now that we applied PCA, let's move on to preparing the 3D plotting. So here, first we will create a fig element. That's of course here, plt.figure. Okay, and now we will want to create an axe, which is 3D. So you know the drill, plt.axis equal to projection equal to 3D. Okay, now we will play with the axes and we'll define some elements. So we'll define the maximum x limit, y limit, z limit. Then we don't want to show, for example, the text labels, and we want to give it a title, just to have an idea about what it is. So I will just drop all of this here. Boom. And here it's 3. Sorry about that. So x set limit, I just put 1, but that is totally random. You may not need to do that. The tick label will be erased, and then the title is here. That's it for the preparing the 3D plots in, and now we will actually plot that for the qualitative analysis of this specific part. So that's a convention, the 3 vector. So it's very easy. This one will be the first element, so the main component. Sorry about the hurt. Eigvect, we take the first vector, the second one, and the third one. Very good. And now we'll make first the scatter plot and then the vector. And that's why I played with the axis and plot just one figure, because everything will be plotted on the same graph, which is very important. So for the scatter plot, ax.scatter, and cluster x, cluster y, cluster z, that's why it's very handy to have the panda data frame, and I give it a color of steel blue, which I like, and an alpha of 0.2. And for the quiver, this is a bit, yeah, more full of, how do you say, full of elements. So for a quiver, we need to give them the origin here, and then the endpoint. So basically the origin is the mean of the cluster, okay, so mean x, mean y, mean z, and then the vector of the end of the vector x, y, z, and the same for the 3 vector. So the main vector, which maximizes the variance, is here. That's the second one, and the dark turquoise will be our normal. Okay, so let's see. I prepare and I plot. Okay, and here, sorry about that, I need to delete that to have that as a one pass LC. It's not working. And you see, here we have the maximum variance is here, the second is there, and that's the normal of our cluster. So it's working really nicely, and you now have a very good way to represent both vector and scatter plot. Nice. Now let's define our 2 functions, so DrawPCA and custom PCA. So DrawPCA, we will take the points and cluster ID, and we'll draw, actually compute and draw the PCA for this point and the cluster ID. So first thing first, what I'm doing is I go there and I take exactly my my PCA here. Okay, so choke, choke, and choke. And now, so remember, I put an indentation, and that is for the, how do you say, the PCA part. We need to be mindful that here we pass points. It's not the cluster anymore, but it will be the points that we will compute. And that's pretty much it for this side. Okay, because all the rest is independent. And now we'll pass all the plotting side. So I just take that and I put that here. Okay, very nice. I take all of this, I make an indentation, and I check that the number of cluster here, I want a string. So I put str, and it will be the ID cluster, right? That we'll put here. That we don't need anymore this comment. And all the rest looks fine to me. We will define the custom PCA, and then we will move on to testing it, okay? So the custom PCA, exactly the same thing. I take all of this, and it will take point as well. So up, very good. Okay, so now let's move on to the looping. For this, we first give our image folder. I have an image folder that I created beforehand, and we will make the loop. So for E in range, we'll say 10 images, okay? So first thing first, I will give it a cluster. So I compute the famous cluster here. I take that. I could have put that within the loop, but I prefer to put that outside the loop. So it's cluster of segment.get group of this time E. It's not defined initially. And then we take the function DrawPCA points ID cluster. So in this case, the point will be the cluster, and the ID cluster will be sorry. That's it. And if you want to save the figure, I will not, because I already have them, but I give you here the comment. It's plt.savefig, image folder plus PCA cluster plus string.png, and the number of DPI that I want. Okay, I will comment that for now. So I execute the cell above, no error, which is very good. And now we will plot our PCA. Ready? Let's go. Chuck, 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 chuck. Very cool. So he plotted all the different cluster. You see, cluster 1, cluster 1, cluster 2, and you see the PCA every time if it's working nicely. Yes, yes. Very cool. So that's very handy, and to be able to analyze a bit the result of your PCA on a qualitative side. Wow, we are almost there, and you are really mastering this part about PCA if you went until there, so kudos to you. Now we will move on to a very important part, which is defining feature extraction for eigenvalues normal. The first thing that I want to do is to create 3 new columns in our data frame, which will host first the eigenvalue, the first, the second, and the third, and only the normal, because the other vectors, I don't really need them, or you can extract them based on the normal. Okay, so the first eigenvalues, we need to initialize this specific column in our data frame. Same thing for the normal. So if I do that, you see, I will just paste it here. If I put now PCD, you now see that you have this famous eigen 1, 2, and so on, which is on 0, and still the number of points here. Now we will loop, but before looping I want to time. So t1 equal time.time, and for E in range of, and in that case, if we want to get this, but not for the point, but for the segments, then you do normally length. Let's test it together. Segments 277. So we have 277 clusters. So that's on which we will make the loop. Okay, so that is well defined. Now let's go and put the loop. So first thing first, we take as above the clusters. Okay, only the x, y, and z value for the PCA. Now we will use our function custom PCA on points, because we do not want to plot. That's why I created 2 functions, and we will take that into eigenvalues and eigenvector. So you output, because you output 2 things from the function, we keep that on 2 variables. So eigenval, eigenvec equal to custom PCA of clusters. Okay, and now that's the tricky part that I will need to explain in a bit of detail. We will want to locate exactly within PCD this time. Okay, we will want to locate the lines that are defined by the clusters indexes, okay? And the cluster indexes, as we saw before, if I do, let's say, cluster.index, if it's defined, yeah, we have a type of cluster.index, and that will not be able to be passed within brackets for index search. So we need to do, and that's a lot of lost time if you don't know that, you take the values of the index and it will put an array, and that you can pass within the localization. And the second thing is, we will only want to change, so we locate these rows and we'll also locate the column that we need to change, and the both at once, okay? So for doing that, you can do that with Panda. You pass that all into the lock and you give both index search. So pcd.lock, okay? And there I will give the rows, the row index and the columns index, okay? The row index, then, as I said, I will pass the specific cluster indexes. And for the columns, I will actually pass the eigenvalues, let's say indexes. So here the indexes are name indexes. So eigen 1, eigen 2, eigen 3. And that's it. And now for each of these columns, you can do that in one go. That's what I wanted to show you. Then you can equal that to exactly the eigenvalue that you want to store. And here it's eigenvalue 0, eigenvalue 1, eigenvalue 2. Very cool. And you do the same thing with the vector. Hop, PCD lock cluster index value, this time n, x, and y, and z that we initialized. Eigenvector, the thing here is we want only to take the normals, so it's eigenvector 2, array tuck, chuck, chuck, and from there you keep every time one element this way, okay? And that's what I do here. That's it for our loop. I wanted to show you that because it's very, it can be cumbersome to find these little tricks to be able to work with your data. So T2 equal time dot time, just to give you a rough idea. It's not the most optimized form, but it's the most comprehensible form that I gave you. And as always, I want to print this specific timing to attribute features to segments. And we are good to go. Do you want to see the result of that? Okay, let's run it. It's running really nicely. You see, it takes half a second to make everything nicely and put the features in the data frame. So now, if I just put the data frame PCD, you see that we have our NX, for example, field with different values, and you can export your data set now, which is the final part. And for that, I give you the command as well, which is PCD to CSV result for blah, blah, blah. Float format, the same one, and I just don't want to keep the indexes on the left, else you have a column with all the indexes of your point cloud. So when you output that, what you get is the result of the PCA, which is here, based on DBSCAN, and I will load it to show you in Cloud Compare. So you see we have exactly the headers XYZ, the label of the cluster, eigenvalue 1, 2, 3, and X, and Y, and Z. Okay, I skip the first line, and I extract the scalar field name, X, Y, Z. Here I will put it as a scalar as well. Scalar, 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 and X, and Y, and Z. Okay, apply all. And that is the labels, right? Very nice. And now if we want to see another element, let's say eigenvalue, you have the eigenvalue which are shown here, and the eigen, the normals. You can do that by edit normals, convert to HSV color, and that is the normals. So we see that we have nice normals. So now our point cloud has interesting PCA values. So of course, as you can see here, nothing was normalized on a common frame. So every normalization is done locally per segment. So that's why we have a weird result. But you could always have something which is more generalized to the full point cloud down the line with an extra step if you need that. So here we went deep into PCA and implemented that. You saw all the different 10 steps to go to exporting the data from loading the first segmented point cloud. And this step is very important because that will condition how we will then orient our bounding box that we will extract. So we'll do that into 2 steps in the next tutorial. For now, the action today is, of course, if you did not aside, just implement it as I told you to grasp everything. That, of course, why I don't give the solution, so that you are implementing the thing, because you will see when you implement the little tricks that I'm speaking about. And let's move then to the next video when you're done with this one.